Discovery of fission. A lot of history in this chapter. Mid-1930s, Enrico Fermi, Italian scientist, he tried to synthesize a new element by bombarding uranium with neutrons. The theory was if he could get a neutron to be incorporated into the nucleus, that it might undergo beta decay and turn into a proton, and so then he'd make an element that was one proton larger than uranium, and this would be cool. So here's the idea. Taking uranium-238, adding a neutron, you get uranium-239, which would decay and give you a larger element. Well, he detected beta emission, but he didn't study the products chemically to see exactly what they were, which makes me want to research this and find out why he didn't do that. It seems like something you would want to do.
Why is decay too fast?
Or maybe it was just too difficult, or he got distracted by something else. Who knows? I'm sure there was a reason. So, not too long after that, 3 German scientists, Lise Meitner, Fritz Strassmann, and Otto Hahn, repeated his experiments, because that's what scientists do. People say, oh, I did this and this happened, and they say, ooh, I want to try that too. And they found that the products, they did study the products, they found that the products had several elements that were smaller, lighter than uranium. This is not what Fermi was setting out to do.
Knock them out?
Well, what it did was it split the uranium atom.
Yeah.
And so this was the discovery of nuclear fission. And as the book so mildly states, this discovery changed the world forever. January 6, 1939, they reported that officially neutron bombardment of uranium resulted in nuclear fission, the splitting of the uranium atom. Before this, people didn't think that you could break an atom. Atoms might fall apart on their own. They were learning about that, but that you could actually split an atom, smash an atom. And that's a picture of Lise Meitner. There's an element named after her, meitnerium. Fermi got an element named after him too, fermium. So what's going on with fission of uranium? So the uranium actually splits into barium and krypton. And 3 neutrons are released in that process, along with a tremendous amount of energy, I mean, mind-boggling amount of energy. It's uranium-235 that does this. Less than 1% of uranium is uranium-235. Uranium-238 is the most common isotope. It does not undergo fission. And so this is why there's the big deal about the enriched uranium and the uranium enrichment plants, and is this country doing it, is that country doing it? Because you can't really cause a lot of problems with just naturally occurring uranium. You have to enrich it, you have to concentrate the uranium-235. So this fission was caused by a neutron bombarding a uranium atom. The process releases 3 neutrons. What if there was another uranium-235 atom over here? It could happen again. So here's the initial reaction. Creates 3 neutrons, which could conceivably bombard 3 more uranium-235 atoms, and it could go on and on and on and on. That's called a chain reaction, where the reaction, the neutrons from the fission of one molecule cause the fission of another molecule. And because there's 3 given off, it expands as it goes. This will only happen if you have enough uranium-235 present in the sample. You need a critical mass. So the critical mass is the amount of uranium-235 needed for this to be self-sustaining. And if you have more than that, it won't just keep going, but it will actually explode. And that's the basis of an atomic bomb, is getting enough of this uranium-235. You get the reaction going, and it explodes. I'm paraphrasing a lot of the history, which is very brief in itself, that's given in your book. But the United States was worried, because this was during World War II. The United States was worried that Nazi Germany would capitalize on this discovery. I mean, it was Germans that discovered the fission, right? And that they would make an atomic bomb first, and then we'd all be in a lot of trouble. And so they launched the Manhattan Project in Los Alamos, New Mexico. And you've probably heard of that. And that was a project to create an atomic bomb using nuclear fission. So the first bomb was detonated July 16th, 1945 in New Mexico. That's a picture, a familiar mushroom-shaped cloud. So that bomb had a force equivalent to 18,000 tons of dynamite.
36 million.
That's a lot of tons. Yeah, 36 million pounds of dynamite. Good luck getting that in an airplane to drop on a city, right? It's not going to happen. So, kind of ironically, Germany had already surrendered by then. But, we went ahead and tested the bomb anyway. But we were having trouble with Japan, and so we did end up bombing Japan twice, Hiroshima and Nagasaki, and combined those bombs killed 200,000 people. And, nuclear weapons were in their infancy, and we didn't really know what the ramifications or the long-term effects of these things were. I guess people use war as an excuse to justify doing whatever you need to win. But this was really a horrendous thing that we did. 200,000 people. So nuclear fission can be used for mass destruction. It can also be used in peaceful ways to generate electricity. Electricity is good, right? We like having lights and air conditioners, computers and stuff. So in an atomic bomb, all that energy is released at once. Kaboom. But if you control it, if you release it in a slow manner, you can use it to generate electricity. And in that process, you don't have air pollution, you don't have any greenhouse gases being given off. And so that's definitely a benefit for the environment. In the United States, nuclear fission is used to generate about 20% of the electricity. Some other countries use nuclear power for up to 70% of their electricity. And just to give you an idea of the amount of energy, if you had a pencil-sized cylinder of uranium, this big, and you had a car that could be powered with nuclear power, which of course nobody has that. That'd be bad in an accident, wouldn't it? But if, right? So this much uranium could power a car under typical use for 20 years. Driving it around town, filling up a 20-gallon gas tank once a week. And you keep going for 20 years. That's a lot of energy from something the size of a pencil, right? So think about a coal-burning power plant. A lot of our electricity is generated by burning coal. 2 million kilograms of fuel is needed to generate the same amount of electricity as 50 kilograms of nuclear fuel. There's a huge difference. And when you burn that much coal, you stick all kinds of nasty stuff into the air. So how does nuclear power work? Well, the fission reaction gives off a lot of energy. It generates a lot of heat. So we use the heat that's generated from the fission reaction to boil water and make steam. The steam turns the turbine on an electric generator. So here we have the core of the nuclear power plant. And this is generating heat. And we have a pump that is pumping water around this. It's not contacting the radioactive uranium. It's just going around it, and it's being heated. And then it comes into this tank where it generates steam. This water is separate from the water in here. And here we've got steam, and the steam comes out here and turns the turbine. The reaction is controlled using what are called control rods. So what causes the chain reaction is the neutrons given off in the fission reaction reacting with other uranium-235 atoms. And so the control rods absorb the neutrons without undergoing reaction. And so if you lift the control rods up, the reaction goes faster. If you took them out all the way, it would probably get into a chain reaction and explode. If you drop them down, the reaction shuts down because it absorbs all the neutrons and the thing stops. Of course, there are some drawbacks to nuclear power, nuclear accidents, and waste disposal. And, you know, we look at things like the tsunami in Japan that overwhelmed the Fukushima power plant. And we say, oh, well, this is horrible, you know, all this radiation and is horrible, and why are we even doing this? We should outlaw nuclear power. And yet when you take a scientific approach and look at the scale of these disasters, they're not that bad. They really aren't. I think I read that there are no documented radiation-related deaths with the incident at the Fukushima power plant. Because we have learned how to take precautions. I mean, they got people out. They evacuated. Most of you probably don't remember Chernobyl. I was in high school. No, I was in college. I was in college. I think it was '86. Chernobyl was a big deal. So they were trying to save money. They were doing some experiments on how they could reduce maintenance costs. And so they had disabled a lot of the safety features to do this experiment. Well, the experiment failed, right? And so the thing blew up. But it did not even blow up like a nuclear bomb would blow up. And so it killed a lot of people and it devastated the area. But it wasn't nearly as horrendous as what we did to Japan. And so I think we have this fear of nuclear power because it's scary, right? I remember in elementary school, we had these drills, you know, because it was the Cold War and Russia was going to come and bomb us, right? And we were all afraid of the nuclear weapons, you know, pointed at each other and somebody presses a switch and the whole planet's gone, right? But that's not really what's going to happen. And so we look at nuclear power and we're very, very afraid of it. And it is potentially very dangerous and very powerful, but could also be used for a lot of good. So I would just encourage you to be informed and understand what nuclear power is. Okay, I'll get off the soapbox.